Percolation threshold is a mathematical concept related to percolation theory, which is the formation of long-range connectivity in random systems. Below the threshold a giant connected component does not exist. While above it, there exists a giant component of the order of system size. In engineering and coffee making, percolation represents the flow of fluids through porous media, but in the mathematics and physics worlds it generally refers to simplified lattice models of random systems or networks, and the nature of the connectivity in them. The percolation threshold is the critical value of the occupation probability P, or more generally a critical surface for a group of parameters P1, P2, such that infinite connectivity first occurs. Percolation models. The most common percolation model is to take a regular lattice, like a square lattice, and make it into a random network by randomly occupying sites or bonds with a statistically independent probability P. At a critical threshold Pc, large clusters and long-range connectivity first appears, and this is called the percolation threshold. Depending on the method for obtaining the random network, one distinguishes between the site percolation threshold and the bond percolation threshold. More general systems have several probabilities P1, P2, etc., and the transition is characterized by a critical surface or manifold. One can also consider continuum systems, such as overlapping disks and spheres placed randomly, or the negative space. In the systems described so far, it has been assumed that the occupation of a site or bond is completely random. This is the so-called Bernoulli percolation. For a continuum system, random occupancy corresponds to the points being placed by a Poisson process. Further variations involve correlated percolation, such as percolation clusters related to Ising and Potts models of ferromagnets, in which the bonds are put down by the Fortuyn-Castellian method. In bootstrap or K-sat percolation, sites and/or bonds are first occupied and then successively culled from a system if a site does not have at least k neighbors. Another important model of percolation, in a different universality class altogether, is directed percolation, where connectivity along a bond depends upon the direction of the flow. Over the last several decades, a tremendous amount of work has gone into finding exact and approximate values of the percolation thresholds for a variety of these systems. Exact thresholds are only known for certain two-dimensional lattices that can be broken up into a self-dual array, such that under a triangle-triangle transformation, the system remains the same. Studies using numerical methods have led to numerous improvements in algorithms and several theoretical discoveries. The notation such as comes from Gra 1/4 NBAUM and Shepard, and indicates that around a given vertex, going in the clockwise direction, one encounters first a square and then two octagons. Besides the 11 Archimedean lattices composed of regular polygons with every site equivalent, many other more complicated lattices with sites of different classes have been studied. Error bars in the last digit or digits are shown by numbers in parentheses. Thus, 0.729724, 3, signifies 0.729724 a plus or minus 0.000003, and 0.74042195, 80, signifies 0.74042195 a plus or minus 0.00000080. The error bars variously represent one or two standard deviations in net error, or an empirical confidence interval. Thresholds on Archimedean lattices. This is a picture of the 11 Archimedean lattices or uniform tilings, in which all polygons are regular and each vertex is surrounded by the same sequence of polygons. The notation for example means that every vertex is surrounded by 4 triangles and 1 hexagon. Drawings from. See also uniform tilings. Note: sometimes hexagonal is used in place of honeycomb, although in some fields, a triangular lattice is also called a hexagonal lattice. Z equals bulk coordination number. Square lattice with complex neighborhoods, 2 newtons equals nearest neighbors, 3 newtons equals next nearest neighbors, 4 newtons equals next nearest neighbors, 5 newtons equals next nearest neighbors, etc. Approximate formulas for thresholds of Archimedean lattices. Formulas for site bond percolation. Archimedean duals. Lav's lattices are the duals to the Archimedean lattices. Drawings from. See also uniform tilings. Site bond percolation. For more values, see an investigation of site bond percolation. 2 uniform lattices, top 3 lattices, number 13, number 12, number 36, bottom 3 lattices, number 34, number 37, number 11. Top 2 lattices, number 35, number 30, bottom 2 lattices, number 41, number 42. Top 4 lattices, number 22, number 23, number 21, number 20, bottom 3 lattices, number 16, number 17, number 15. Top 2 lattices, number 31, number 32, bottom lattice, number 33. Inhomogeneous 2 uniform lattice. This figure showed the 2 uniform lattice number 37 in the isoradial representation, in which each polygon is inscribed in a circle of unit radius. The squares in the 2 uniform lattice must now be represented as rectangles in order to satisfy the isoradial condition. The lattice is shown by black edges, and the dual lattice by red dashed lines. The green circles show the isoradial constraint on both the original and dual lattices. The yellow polygons highlight the 3 types of polygons on the lattice, and the pink polygons highlight the 2 types of polygons on the dual lattice. The lattice has vertex types, 33, 42, plus, 3, 4, 6, 4, while the dual lattice has vertex types, 46, plus, 615, opening round bracket 53 closing round bracket plus opening round bracket 6 over 15, 52, 4. The critical point is where the longer bonds have occupation probability P equals 2 sin equals 0.347296, which is the bond percolation threshold on a triangular lattice, and the shorter bonds have occupation probability 1 to 2 sin, I/18, equals 0.652703, which is the bond percolation on a hexagonal lattice. These results follow from the isoradial condition but also follow from applying the star triangle transformation to certain stars on the honeycomb lattice. Finally, it can be generalized to having 3 different probabilities in the 3 different directions, P1, P2 and P3 for the long bonds, and 1, P1, 1, P2, and 1, P3 for the short bonds, where P1, P2 and P3 satisfy the critical surface for the inhomogeneous triangular lattice. Thresholds on 2D bow tie and Martini lattices, to the left, center, and right are, the Martini lattice, the Martini A lattice, the Martini B lattice. Below, the Martini covering medial lattice, same as the 2x2, 1x1 subnet for Kagome-type lattices. Some other examples of generalized bow tie lattices and the duals of the lattices. Thresholds on 2D covering, medial, and matching lattices. 4, 6, 12, covering medial lattice. 4, 82, covering medial lattice. 3122 covering medial lattice, equivalent to the Kagome subnet, and in black, the dual of these lattices. Left, covering medial lattice, medial dual, shown in red, with medial lattice in light gray behind it. Thresholds on subnet lattices. The 2x2, 3x3, and 4x4 subnet Kagome lattices. The 2 subnet is also known as the triangular Kagome lattice. Thresholds of dimers square lattice. Thresholds of full dimer coverings of 2-dimensional lattices. Here, we are dealing with networks that are obtained by covering a lattice with dimers. In discrete mathematics, this problem is known as the perfect matching or the dimer covering problem. Thresholds of polymers on a square lattice. System is composed of ordinary random walks of length L on the square lattice. Thresholds of self-avoiding walks of length K added by random sequential adsorption. Thresholds on 2D inhomogeneous lattices. Thresholds for 2D continuum models. Equals critical total area for disks, where n is the number of objects and L is the system size. For ellipses of semi-major and semi-minor axes of A and B, respectively. Aspect ratio with. For rectangles of dimensions and. Aspect ratio with. For power law distributed disks with. Equals critical area fraction. Equals number of objects of maximum length per unit area. For ellipses, for void percolation, is the critical void fraction. For more ellipse values, see. For more rectangle values, see. Thresholds on 2D random and quasar lattices. Theoretical estimate. Thresholds on slabs, more for SC open BC in ref. H is the thickness of the slab, HXAXA. Thresholds on 3D lattices, filling factor equals fraction of space filled by touching spheres at every lattice site. Filling fraction equals filling factor PC, site. NN equals nearest neighbor, 2NN equals next nearest neighbor, 3NN equals next nearest neighbor, etc. Question: the bond thresholds for the HCP and FCC lattice agree within the small statistical error. Are they identical, and if not, how far apart are they? Which threshold is expected to be bigger? Similarly for the ice and diamond lattices. Thresholds for 3D continuum models, all overlapping except for jammed spheres and polymer matrix. Is the total volume, where n is the number of objects and L is the system size. Is the critical volume fraction. For disks and plates, these are effective volumes and volume fractions. For void, is the critical void fraction. For more results on void percolation around ellipsoids and elliptical plates, see. For more ellipsoid percolation values, see. Thresholds on 3D random and quasar lattices. Continuum models in higher dimensions. In 4D. In 5D. In 6D. Is the critical volume fraction. For void models, is the critical void fraction, and is the total volume of the overlapping objects. Thresholds on hypercubic lattices. Thresholds in higher dimensional lattices. Thresholds on hyperbolic, hierarchical, and tree lattices. Note: M, n is the Slur currency Flees symbol, signifying a hyperbolic lattice in which n regular m-gons meet at every vertex, Cayley tree with coordination number z, PC equals 1/, Cayley tree with a distribution of z with mean square PC equals. Thresholds for directed percolation. Nn equals nearest neighbors. For a dimensional hypercubic system, the hypercube is in d dimensions and the time direction points to the 2D nearest neighbors. Exact critical manifolds of inhomogeneous systems, inhomogeneous triangular lattice bond percolation. Inhomogeneous honeycomb lattice bond percolation equals Kagome lattice site percolation. Inhomogeneous lattice, site percolation, or, inhomogeneous Martini lattice, bond percolation, inhomogeneous Martini lattice, site percolation. R equals site in the star. Inhomogeneous Martini A lattice, bond percolation. Left side. Right side. Cross bond. Inhomogeneous Martini B lattice, bond percolation. Inhomogeneous Martini lattice with outside enclosing triangle of bonds, probabilities from inside to outside, bond percolation. Inhomogeneous checkerboard lattice, bond percolation. Inhomogeneous bow tie lattice, bond percolation. Where are the four bonds around the square and is the diagonal bond connecting the vertex between bonds and percolation thresholds of graphs? For random graphs not embedded in space, the percolation threshold can be calculated exactly. For example, for random regular graphs where all nodes have the same degree k, PC equals 1 per caret. For ADASA-Ra copyright ME graphs with Poissonian degree distribution, PC equals 1/. The critical threshold was calculated exactly also for interdependent ER networks. See also, percolation, percolation theory, graph theory, percolation critical exponents, 2D percolation cluster, directed percolation, effective medium approximations, epidemic models on lattices, uniform tilings. References